Good afternoon, everyone, and welcome to today's EOL seminar. I'm Sarah Woods, and on behalf of EOL, I'm pleased to introduce Dr. Jothiram Vivekanandan. As many of you know, Vivek is a senior scientist at NSF NCAR's Earth Observing Laboratory. His research and development breadth includes polarimetric radar, dual wavelength radar, phased array radar, lidar, and microwave radiometer. He is a fellow of the American Meteorological Society and an associate editor for Radio Science. The 2018 European Geophysical Union's Christian Huygens Medal was awarded to Vivek for his pioneering and groundbreaking work on the microphysical characterization of clouds and precipitation using advanced remote sensors. Prime examples of his leadership are his development of a dual wavelength radar system created by adding a millimeter wave radar to the NCAR's S-band polarization radar, SPOL, and his scientific and technical leadership to the development of an NSF-funded cloud radar for the Gulfstream 5 research aircraft. Vivek led the composition of the NSF MSRI-2 Airborne Phased Array Radar, APAR, proposal project description, working closely with the APAR team. The project description made a clear and compelling case for the need for APAR, resulting in NSF funding the $90 million APAR project, for which Vivek is the APAR Science and Engineering Liaison. APAR is a dual Doppler and dual polarimetric weather radar system on the C-130 aircraft, which will enable more accurate weather forecasting. It is a transformative technology for weather remote sensing with several novel ideas and concepts. Please join me in welcoming Vivek for his seminar titled Sensing the Onset of Collision-Coalescence and Drizzle from Joint Lidar and Radar Measurements. Quick reminder for those of you online, you can enter your questions in Slido and we'll take those at the end. Vivek, welcome.
Thanks, Sarah, for the nice introduction. This topic, onset of drizzle, is a well-researched area. I'm a newcomer to this area. My interest has been, could you do that more quantitatively, not just qualitatively? Cloud-Drizzle Transition, that's the whole purpose of this exercise today, the seminar. So I'd like to acknowledge my co-authors for the presentation, Alexander Kozanski from MTU, Michigan Technology University, and Dr. Huang, and they'll help me quite a bit with many of the presentation slides in this one. This presentation has 3 parts to it. The first part will deal with the electromagnetic simulations of stratocumulus cloud. That forms the basis for how do we develop this technique for both lidar and radar. Second part will involve, we use that technique so that we could basically do the particle ID. Particle ID is a standard product, part of the cloud radar or USPOL radar currently in the NCAR. And so you could have particle ID based microphysics. Then third part, to simplify, once you understand the first 2 parts, EM scattering, electromagnetic modeling, the second part about particle ID, third part about transition of cloud to drizzle. That's the theme of the presentation here. Stratocumulus cloud, in this case, talking about clouds like very shallow, with even boundary layers, and they are very prevalent. In fact, plays a huge role in climate science feedback. Cloud. It's important cloud to study. What are the science drivers? The drizzle itself influenced by various factors. For example, if high concentration of aerosols will suppress the drizzle. And the drizzle developed only when turbulent mixing exists like that. Then the drizzle is a very complex process, how cloud become a drizzle, then become a rain. And it's a very complicated process. Stratocumulus clouds are a dominant cloud type. Like 60%, 40-60% of the planet covered by this type of cloud. And this cloud is quite important in terms of understanding the microphysics. What kind of cloud droplets, liquid water content, all those things are quite important for this type of cloud. Basically, in EOL, we have instrumentation. Our objective most of the time is understand the microphysics, modeling, so that we can improve retrieval of either cloud liquid water content, ice water content, or cloud droplet size. These are the products we produce for scientific community. And so currently, there are power law relations exist. They are good, but they're restricted to small reflectivity range. For example, it's only for clouds. It may not apply to drizzle cases like that. It's very restrictive. That's one issue. But a lot of sort of work has been done in this area. And also, there are, based on Doppler measurements, like Doppler spectra, where the skewness in Doppler spectra is used, distinguish between cloud droplets and drizzle droplets. And there are various techniques. The method what I described today is based on just backscattering, lidar, radar. There's no Doppler involved in this one in terms like cloud Doppler spectra in that detail. Quite simpler. When you get into NCAR, what is it NCAR currently? NCAR planning to preparing for a next strategic plan, 25 to 30, I guess, 5 strategic plan. There are a number of overarching questions. One of them is high impact weather, cloud mode simulations, where all these play a huge role. Then they lead into what kind of observations will help this kind of strategic plan or answering science questions. And so what can we do? And this is a presentation where we see the latest instrument what we have on a G5, radar and lidar, will contribute quite a bit to this kind of work, what strategic plan planning to do that. And a lot of things will be quite helpful to do in the coming years. Just give an introduction here. Say currently if you look at the literature, the power law relations are used for liquid water content. We have this kind of DBZ power law. It exists only if you have it like certain thresholds and certain area. And it's very restrictive. It's like it's fine-tuned or tuned to one case, other case. It won't work for other places. That's one problem with that. For example, even droplet size. For only cloud droplets, it will work. Like in this case, it's the effective radius valid like some kind of DBZ and power law relation, like if you see it. And so these are the current status. And so we don't have a technique where it works very broad area, broad range of reflectivity and lidar measurements. Now, that means, in summary, if you look at it, currently what we face, most of them assume a mathematical from droplet spectra. They're Gaussian or exponential, log normal like that. And that itself is a restriction. Why it should be exponential, why it should mathematically it should be Gaussian, log normal like that. It's a convenience, we use it. Again, like I showed, it's all valid only restrictive range of reflectivity or lidar measurements. It's not much larger than that. So currently what I use is our own instruments. In EOL, we have HCR, HSRO. Just to introduction here, the hyper cloud radar is cloud radar with 94 gigahertz, 3 millimeter wavelength. It measures about 37.5 meter. In fact, we can do our sampling with 20 meter resolution. In that 20 meter, we get very good measurements for every 10th of a second. 10th of a second is quite good on an airborne platform like a G5. For about 150 meters per second, talking about a lot of good measurements in this kind of situation. Then we have the high spectral cloud lidar. This is at a visible wavelength, the half a second dwell time, the 7.5 meter resolution. So these data sets, when we collect them, we try to put them together in a 20 meter resolution along the range, half a second along the entire track. That means measurements, what we get from these measurements are fantastic. They're very good, well calibrated. For example, the HSRL is a calibrated lidar measurement because it measures absorption, optical depth. Most of the radar we got to correct for the scattering or losses, but HSRL is a very good instrument in that way. It's already corrected for absorption or scattering losses. Okay. What are the issues are, if you look at it, the issues are diffuser reflectivity on the y-axis here, liquid water content. This mainly is all liquid droplets. I'm not talking about any ice cloud in this case, all liquid droplets. If you add reflectivity, then for a given reflectivity, it could be the red represents cloud droplets, green is drizzle droplets. See, there is an issue. If you know it is cloud or drizzle, they can estimate liquid water content in a reasonably good. Otherwise, you don't know where it is. It's a large variation there. That's the problem. To solve that, we need to understand scattering characteristics very carefully or precisely. So what we have done is we come up with simulations of liquid water droplets here. And the x-axis shows the microns up to about a millimeter or 10 millimeter here we're talking about. Then the y-axis is normal cross sections. And the blue is the backscatter. The red is extinction. And green is a ratio between scattering and extinction. So these are the standard calculations using just a spherical droplet size. In this case, no shapes in this one are just spherical. And the other panel, the right panel, shows the LiDAR scattering cross sections. So in the LiDAR, if you look at it, they are mainly optical scattering. And the red line here is extinction here. The extinction is, if you look at it, basically it's a factor of 2, which is basically is called extinction paradox. That's how it is. If you look at scattering books, will contest why the extinction paradox like that. Same thing with the radar. The red line shows saturation after about more than 10 millimeters or so. You'll see those kind of stuff. And so then the blue line in the LiDAR, there's a ratio basically, the green line at the top, the ratio between extinction to scattering, that's a green line there, that shows about factor of 20. That's basically used to distinguish the cloud droplets because that's very well known in LiDAR scattering people. Same thing with here also we have, in the radar also we have a flatness for the large particles. We aren't making use of some of those at this point, but there are possibilities you can use that. And so once you have this electromagnetic scattering model, what we did was, during the WAMOS, this is like a long time back, about 2008, C-130 collected a fantastic in situ probe measurement using a cloud probe and drizzle probe. This about 4,000 droplet spectra ascending and descending within a stratocumular cloud. Then this well quality controlled, the 1 second measurement, the cloud probe data about 30 bins between 1.2 micron to 5 micrometer. Again, a drizzle probe 62 to 1.575. This is fantastic measurements, quality control. Jon Jensen basically worked on this for a long time back. And we use that as an input for simulating stratocumulus cloud parameters. Once we did that, the LiDAR simulations, when we did that one, then basically came up with a definition of a size. Say, for example, in a cloud, for a given liquid water content, when the cloud drizzle transfers happens, what happens in this case is a small droplet, less than about 30 or 20 micron cloud droplets, becoming a big droplets. That means dB is going to increase. That's all to it, right? Particle size become bigger. And we have to have a characteristic size which could distinguish particle size. What it is that 10 micron? Is that a 50 micron? Could you tell that without using in situ probe? That is the whole purpose. The top panel shows a new or characteristic size called radar-estimated diameter. The x-axis shows radar to radar reflectivity. It's just a backscatter measurement, that's all to it. 45 dB dynamic range shows we can basically estimate a size between less than 10 micron all the way to 160 micron. That's a key measurement. Because this RLED is defined just using remote measurements. It is not a MED. People used to with that. In the bottom we have MED panel. The D effective, which people use it very often. These things are related to RLED. Okay, you can say RLED is because it's related to reflectivity and lidar ratio. It emphasizes the tail end of the spectra, DSD spectra, whatever you have it. That means it has a potential to detect the tail end, which is the drizzle droplet formation in a cloud volume like that. And that is a really important quality or important parameter of RLED. The RLED is larger than a D effective, as you see it. Then MED, again, RLED is larger than MED. But if you look at a narrow distribution, say, not broad, narrow distribution, they're all same because there is no statistics there. But if you get a broader distribution, there are differences. Hence, we can relate the RLED to MED or D effective if necessary. Could be done. That means we have a bridge where remote measurement, we can measure droplet size. In situ probes, can measure droplet size, but that could be bridged if necessary. Why want to do that? Because remote measurements are widely applicable to various places, various time zones compared to in situ measurements, where it has not only is going to look at just a small area of like a cloud measurements, most of the volume comes in drizzle drops. I mean, ubiquitous. That's always a problem. And that's why the problem with relating in situ measurements with remote measurements. People have looked into many years, nothing new about that. Once we have the RLED, the big graphs RLED, the green is basically related to drizzle drops. The red here, the cloud droplets. See, it clearly distinguishes between two regions. That's the key. But on the top, as reflectivity here, it's not the case. There is always overlap. Hence, there is the RLED using a lidar measurements, we can clearly distinguish between drizzle and cloud droplets. So we use this parameter. Once in droplet size, it gives a much more accurate retrieval of liquid water content. Let me show you that. The left panel shows the RLED on the y-axis, lidar ratio, what could be estimated using just a backscatter measurement. That's all to it. That given as a 9.12 times Z over beta. Beta is a lidar backscatter. Z is a radar backscatter. So 0.25. Because like a d power 6, beta is a d squared. It's a 1/4. That's all to it. As simple as the physics. It's nothing complicated. And the right panel shows liquid water content in terms of normalized reflectivity using RLED. This is like in the case of S-pole radar, we use a Z and ZDR to improve rainfall estimates like that. Same thing here. We have the size. ZDR estimated, it's kind of size. Same thing with the RLED, we have it. Using that RLED, we're able to estimate liquid water content. How good we can do it? Okay, this is a kind of summary here before I get there. The RLED is basically it's a reflective ratio between radar and lidar. The normalized reflectivity. LWC is a linear relation to normalized reflectivity. That's all to it. There are three simple equations. In fact, a PhD student from Arizona recently asked me, how come so simple? I want to use that technique to do that. And he's working on that. Some of the advisor said, well, go and look at satellite measurements. We want to do some other stuff like that. The answer is quite simple. It doesn't have any other, approximations or other issues with that. Okay, this is a cross section or during the CSAT in 2015. The G5, the top panel shows DBZ measurement W-band radar. The second panel shows the lidar observations, beta. And the bottom two panel shows, the top one shows the RLED, 10 micron to 500 micron here. The bottommost panel shows liquid water content. You can see how clearly it shows the cloud layers, which is about say 3 to 4 minutes there. If you look at it, see the beta ladder packets so strong. I don't know, I can get my cursor here, but in that case, we got a very small liquid droplets like that. Then contains a lot more liquid water content. And it basically gives what you expect to see in a cloud base, where you got a cloud droplets, a lot of liquid water content, small droplets. At the same time, here is a shower. There's a much bigger droplet sizes, small liquid water content.
Excuse me, I'm sorry. If you step away from the mic, we can't hear you online.
Yeah,
Sorry.
okay. Because I can't use my cursor, that's a problem.
There's a cursor there.
Yeah. Okay. So what you got is just an example. This is about 42 kilometer swath as the G5 flew for about 5 minutes. Looking at various types of cloud here. The cloud between very low dBz or is higher dBz. But all these cases, we use those 3 simple equations to come up with RLED, droplet size, liquid water content. Then, how do you know it's right? In the CSAT, we have only one airplane, but G5 at a radiometer, got GVR, 183 gigahertz. That estimates the total path of liquid water content. So this is a comparison of the red line is a radiometer, the blue is a lidar estimate. The RMS has a 0.1 millimeter when you compare it. And these are 2 independent measurements. One using active lidar measurements of liquid water, other using the radiometer. Totally independent. And so given that footprint size are different, for example, radiometer takes 6.5 seconds to get a measurement. Radar takes half a second measurement. And so you got to do many averaging, but even in spite of all the averaging, different footprints, still the comparison seems to be very good. This was published in JTech about 2020, got very good reviews for this paper. In summary, having that EM model, we're able to come up with retrieval technique where you can estimate the droplet size and also liquid water content where they validated. We did not validate RLED, okay, but RLED is used to estimate liquid water content, that's been validated. But interesting thing is, the WAMOS was conducted in 2008 in Southern Pacific, the 4th bullet here. The technique what we used in Southern Pacific, using those in situ probe measurements, EM model, is elaborated to Northeastern Pacific in 2015. Things does work because based on the physics. And so this is no geographical tuning, anything to do with that. It's a stratocumulus cloud, that's all to it. We did that, it still worked. And so the main thing is the technique what we developed, it does work independent of geographical region. Then inclusion of the size extended the usefulness of remote measurements, lidar measurements, that we can have a very broad, we don't restrict only to certain reflectivity values. This is my second section. The first section mainly EM modeling, RLED, how useful liquid water content. These are very key to do that for detection of drizzle transition or cloud-drizzle transition. If you want to get the particle types, we use fuzzy logic, not thresholding boundaries, because thresholds are rigid boundaries misclassified, because in the remote measurement, there's sort of overlap, like a cloud drops and drizzle drops, they overlap. Ice and liquid overlap. And we cannot use the thresholds. We use a fuzzy logic algorithm to do that. Neural network, other people try to use this one. It equals extensive truth database so that you can train neural network to do it. Again, if it doesn't work, we don't know how to make it right. What we use is overlapped, smooth transition exists. Hence, fuzzy logic schemes are very good for this kind of applications. What's the fuzzy logic compared to digital logic? Digital logic is 1 and 0, a set and a complement as a null set, that's all to it. Fuzzy logic, the set and the complement is not 0 set. It has some overlap. For example, cloud, drizzle. There's always a transition happens. Drizzle to cloud transition happens. Liquid and ice, there is a melting region. And that's how we used it. Then this has been, we have done this long time back for NCAR for S-pole radar measurements. That's currently used in S-pole measurements for a microphysical detection, like between hail and rain, various grapple and rain, all things. The currently standard product in NCAR. Then we use that technique. Come up with a PID algorithm. A similar technique used to come to PID algorithm. We used about basically both radar and lidar measurements plus temperature, but 6 measurements. The output categories are raindrops, drizzle, cloud drops, small frozen, large droplets like that. Then in this case, there's no frozen droplets. It's very simple compared to what we used to do that. And so we use these fields to come up with a particle ID. There's a very good paper, Ramatash and myself, we published in 2022, Earth and Space Science. And this is applied to the test and CSAT. What we see here is 3 major types of liquid droplets, the cloud, and the drizzle, and the rain. In this work focuses on, could we extend this cloud and drizzle transition? This is the problem. How can you do that? That is one of the challenging problems, how you do that. That is not that easy to do it. It takes a lot of work. You can understand, drizzle is a big DBZ, cloud small DBZ. What of the transition, between cloud to drizzle? What happens with that? What we did is, we come up with a lot more EM scattering. Here we have on the x-axis the DBZ values, on the y-axis absorption, attenuation. This attenuation could be measured various ways. If there are 2 radars, we can do that directly. Or there are other ways to do that. Using a pump power relation, you can use it with simulations. Use the cloud probe measurement, PC probe measurement, what I described earlier in the WAMOS, the same thing were used. The red belongs to cloud droplets. The blue is the drizzle droplets. The region in between the green, that's the transition cloud to drizzle. Hence, we need to have attenuation somehow. We can do that thing. So we use the same measurement what I showed you earlier. Same measurement I used it. This is that 5 minutes of CSAT measurement, 2015, July 24th. The top panel shows basically a aerosol backscatter coefficient LiDAR measurement. The middle panel is radar observations. The bottom panel is the absorption attenuation measurement. Okay. Once we use these things, there is a result. Again, I'm showing the DBZ measurement, radiative velocity, the spectrum width. The bottommost panel of interest, it's a yellow color, shows cloud drizzle transition. How do you know it's right? I don't know really, but logically it fits okay, that's all to it. Okay, if there are some measurements where I can validate, we can do that. But I'll show you some examples how I can apply this one. And so you can see, this basically the blue is a cloud, then green is a drizzle, then red is a rain, it does that. Then there are regions where you can see the yellow color around. That is the transition region where this cloud to drizzle happens. Okay. Now let me summarize what I showed you so far today. A PID algorithm based on fuzzy logic. We did a lot of work on this. We published a papers on that. Ramatash and myself published a paper. Use the same product, which is standard product, except we extended that to do the cloud drizzle transition. Now, if you want to go to a little bit deeper, what is this Cloud-Drizzle Transition like that? I showed you earlier, we got about 4,650 1-second droplet sector existed. This is the histogram of that one. The top panel shows basically the concentrations and the mean diameter. This from a cloud probe, Drizzle probe. It's all in situ probe measurements from workers. You see 130 measurement. The bottom shows the lidar backscatter, the radar backscatter. What is interesting here? The green, right? The green corresponds to drizzle. The blue is cloud. See how in the lidar backscatter compared to radar backscatter, they're switched basically. That gives a advantage of RLED because we're using the backscatter from lidar, back from radar measurement. That's what's used to compute the droplet size. That means the RLED is taking not just one size here. It's extending from the small droplets to big droplets. It covers a large range. That's how it is. And so RLED, based on radar measurements, gives a very clear distinction to how to estimate a particle size. This is independent of any mathematical form. It's a Gaussian or modified Gaussian or exponential, it doesn't matter. All you need is two measurements, you can estimate that. You can relate that to MED or D effective if necessary, because the people work in both areas, in situ and remote measurement. We can relate that if necessary. Okay, for the what I showed before the DBZ, the 5 minutes, same measurement, right? Now I am showing you just focus on RLED. See how the RLED is done, like you got this 10 micron up to 500 micron. We have various small clouds here on the outer 1916. They're all mainly very small droplets, but there are like a shower in that about 1918 or something like that, 1918, where you got about 1917, 50 or something like that. We see the bigger droplets like that. RLED does all those things like that. It can basically extract the size. Why is so important? Once we know the size, then earlier I showed liquid water content. Then you can estimate the concentration if you want, because pi d cube, you can assume this basically is a d, pi d cube 6, mean diameter, liquid water content, comes concentration, as simple as that. All these schemes what they use for microphysical parameterization, they need all these parameters, the size, liquid water content, concentrations, all to be retrieved using the technique what I'm describing today here. Now, if you use this one, the RLED, the stratiform cloud, all the way goes from very small size up to about 3 or 400 micron here in terms of Z and beta. And I extended what I did in the cloud probe. In the beginning, I showed you like this. It's only up to 160 micron. That all depends upon in situ probe, what is simulated. Now, I was able to extend the range of RLED. The y-axis went up to 160 micron here. Now, I can went up to even about 400 micron. This is a big difference. And so you could estimate the size, even broader area in an average sense. Remotely, I don't know anyone really does this kind of way, estimating a size using just remote measurement without assuming any other spectra or anything like that. Okay. Once we did that, we applied, looked at how the RLED look like that, okay, using remote measurements. The blue is a cloud, yellow is a cloud and drizzle. See how this RLED, logically it fits. Compared to cloud and drizzle are much larger. The next panel shows cloud and drizzle, same thing as previous panel. The drizzle, again the drizzle much bigger. The third panel shows the drizzle with the rain. And this, basically, logically it fits, but there's some overlap. If you define cloud of less than 50 micron, Of course, I'm showing 50, in the top panel, the droplets which are more than 50 micron. Okay, but this in cloud probe, you can characterize something, but in terms of remote measurement, they're different. We got to try to bridge that gap. That's not done yet because people use remote in-situ measurement, remote measurement. There is a bridging has to be done. Then we can do that. Means the retrieval technique, what I described here, shows we could retrieve the particle size using reflectivity of radar and backscatter coefficient HSRL. That's good enough to retrieve that. Then using that, DBZ, RLED is liquid water content. Then once you do that one, it's concentration. I haven't shown concentration, I'm not going to show it today, but it's a matter of time to show some of the results like that. Now comes question, okay, the RLED is a droplet size. Logically what you feel, bigger the droplet, broader the distribution, DSD, much broader, like a cloud droplets. Much smaller RLED is DSD or standard deviation DSD, much narrower. If you look at rain or drizzle, it's a little broader because it contains a lot more bigger drops. DSD much broader. It's well known, nothing new about that. We looked into those spectra, what we collected from what we got from RAF, Don Jensen gave us. What is the DSD standard deviation compared to RLED? That's the result here. This is all 1 second measurement here, 4600 or 4600 droplet spectra here. The blue is the cloud droplets. The pink or magenta color, drizzle droplets. The cloud and drizzle combining, that's the middle thing. What shows the RLED in the x-axis? Standard deviation of droplet spectra. Okay. This is important information because it's not only mean size. People want to know, also there's a need to understand what the width of the spectra. Could you say it? You can do that. Hence, but I'm showing with the in-situ probe measurement. I don't intend to validate any of those things. But it seems to be logically it fits how the cloud, the drizzle in the top panel, then drizzle and cloud together, you got a lot of scatter. Could be done. Hence, we have a RLED. I can fit a line to this, come up with the DSD spectra, DSD standard deviation, we can do that. So what is described so far is a very quantitative way how we could use radar measurements, well calibrated, come up with stratiform cloud microphysics. How do you apply this thing to our future work? Like I described earlier, NCAR strategic plan looking at modeling across scales, cloud and weather scales. They need a lot more information for either it is parameterization schemes. We can compute statistics of the macro physical. We can do that. Liquid water content I showed you, we can compute for like stratiform clouds. RLED, the size could be done. Number concentration could be computed. And if you compute this, you're not going to develop anything new parametric scheme. There's so many out there in the literature. We can validate using our observations. And that is the key. In a strategic planning in NCAR, they're asking, what we could do with the new instrumentation, what you can do with that, with the modeling across the scales. Then yes, of course, modeling across scale could be done. It's a technique what I described here. We can come up with all those microphysics parameters. We can validate some of those and also come up with tuning those parameter schemes because all depend upon auto conversion. How the cloud droplets become drizzle droplets. Auto conversion, a lot of equations are out there in the literature. How good are they? But we have fantastic measurements from CSAT. It's all warm clouds. There's no ice phase. And there's not much complicated. So this is one area I thought in the future, EOL can do that, provided we have enough resources to do this. We have tons of data, well calibrated, and we can come up with all this parameters. Could be done. Okay, all I talked so far is only liquid cloud. I haven't touched about ice cloud. What you can do ice cloud? Ice cloud is important too. Quite a ice cloud present many places. How do you do that? Currently, we use linear depolarization ratio, detect the ice cloud. But a lot of people working on this many years, we can detect the ice cloud. Could we say about particle size or ice water content, vapor, ice mixed up, all those things could we say anything like that? So difficult to do, just the one radar measurement, we cannot do much. And so if you want to extend what we can do, the one way is, of course, you can go for one more radar, a Ka band radar we thought about, we can do another part. We can do that. But there are other things also in the literature. Look at a community, what they're going to do. DLR in Germany, they have G5, same as us. What they are planning to do this kind of work, climate studies, what they are planning is ice microphysics, spectral imaging multi-camera systems. This is basically a bi-directional scattering. That could be used for energy budgets, for force and precipitation, and come up with particle types and also particle size. This is well studied in a case-by-case basis. Now the DLR is planning to implement this camera, which is about 2D radiances. There's a lot of good literature out there. It's all a passive measurement. It's not active measurement here. This is that costs about 300K. This kind of camera, we can do that. Between 500 to 1650 nanometers, you can detect some of those force and precipitation. And this is terabytes of data. They are quite good for estimating various ice particle characteristics, frozen precipitation. Then other one could be a sub-millimeter radiometer. Compared to visible IR, if your radiometer is between 183 and 448 gigahertz, 14 channels, that could basically give us more about ice particles, water profiles, particle diameter. A lot of ice particle distribution could be done. This is people organized research area here, potential to do all those things. That's about $2 million. Could be put another part. Instead, DLR is planning to do some of this in the coming years. Having some other, they have a radar also. They have a K-band radar and other instrumentation, institutions, all those things we have. But in addition to it, planning. And you can think about this around, compared to radar, it's less expensive, no moving parts, but it's a different area of research. It's more into passive sensing. But the techniques are well studied in the literature. Someone could easily learn. I have done a lot of radar radiation studies myself. I'm not using it here because we don't have that much instrumentation, except RAF as MTP, temperature profiling. Also, they measure the visible IR radiation for energy budget. But these are 2D radiances. That gives a lot more. That's why 6 cameras, basically use it for multiple bands. They can measure that. There are a lot of studies that went into that. That could be quite helpful. Then again, sub-millimeter radiometer at much higher frequencies, much deeper into clouds compared to visible measurements. So that is my last presentation, last slide, I'm sorry. And just for a reference, citations, we have the paper we published in JTech some time ago. Then Earth and Space Sciences, the paper mentioned about particle types. Then we have other paper mentioned in the presentation about radar, radiometer, like that. So with that, I'm happy to take any questions.
Thanks, Vivek, for that really interesting seminar. As an in-situ person, I learned a lot. Does anyone have any questions for Vivek?
I'll start. It was a great talk, Vivek. A comment, we rely on our in-situ probes to understand processes and relationships and different properties to each other, but I think we, especially on airborne missions, we tend to not think about these integrated measures, and having them both at the same time, I think, is really critical for us to do things like you suggest, use this data for validation of parameterizations and like. So I just really like the approach. My question is about where this is applicable. You're looking in, at least for the worm cloud, you're looking in stratocumulus, which I'm assuming is easier for you to target because you have some kind of homogeneity, but because this is active remote sensing, you have a narrow field of view, you know, what's the applicability in broken clouds and the like?
Good question. Stratocumulus cloud, it may look as if it's homogeneous, really it's not. It has a lot of variations in that when the cloud it
But
changes.
it's not broken.
Yeah, it's not that homogeneous compared to, of course, like thunderstorms. It's a lot more easier to deal with that. That technique, what I described here, really it uses just a spectra of a liquid cloud, basically droplet and drizzle droplet. That's all to it. So I'm not using ice phase in this. That's only limitation. It's anything liquid phase, whether it is in a convective cloud annual, if there is anything like that, or any other cloud, warm cloud, could be applied. And the technique really, it doesn't know what cloud I'm using it because the simulations are just EM scattering simulations, liquid cloud. We know rain droplets are liquid droplets are battery constant, very good, other things like that. And it could be applied to other things. I'm making it much simpler to begin with because the CSET data and also the data sets, other programs, what we have, then those are very good data sets where lidar radar measurements we have already. And we could, with some resources, we could work on that, produce a good validation scheme, see how good those microphysical parameterization schemes. This is the one way you can validate some of those, and because most of them developed using some assumptions, in situ probe measurements. I don't know how much use the remote measurements. They're very limited. I thought some of the what we have here, it's a matter of how much time and energy we have to work on this data set. Other data, because in my experience, I'm sure all the people here in remote sensing measurements, 90% of the work goes into calibration, data quality, all those things. Once we have that, then we have a good technique. Then I thought it's a bit smoother to look at all those parameters. And so I would start with simple statistics. See whether all, because what I showed just a 5 minutes, 40 kilometer. It got a lot more for a convinced scientist. Is it really that useful? We have to do that at some point, provided there is enough resources. In this what I showed, the 5 minutes data, but 42 kilometer, it contains a small cloud, a big cloud, the cloud with the drizzling, other things like that. And it has many features, but still, we could work on more of this data set to show, yes, it does make sense. Thank you.
Thanks. Anyone else in the room?
Thank you. It's very encouraging to see these used together. The question I had was, to what extent can you make use of the vertical velocity data as an additional parameter to either resolve the spectra better or to relate it to the vertical characteristics of the cloud, such as entrainment and that sort of thing?
Okay. Yeah, very good question. What we measure is droplet velocity, weighted by the dBs, as very well known. There one more variable, which is called ambient velocity. It has to be corrected for that. And there are techniques using Dr. Spectra. Rika is working on some other techniques. You could comment on that also. And so for a PID, we use fall velocities for doing that. Colliers and Luke, and they use basically Doppler spectra to distinguish between cloud drop versus drizzle drops or things like that. Skewness in the Doppler spectra could be done. And that bit more inward could be done. It improve, like for example, I showed you basically it's a spectrum width of the Doppler movement. I didn't make use of any of those. How to interpret it? Spectrum width is important when the drizzles set in, right? I won't really interpret some of those, but those things exist. I won't spend much time with that. Yes, we could do that, and that will add more value to it. How we can make use of the Doppler studies. But what I present is quite simpler. Just a backcut measurement, not to worry about. As well calibrated, you can use it. But if you add other measurement, get adapter, it will improve the understanding of any other things also. Because the first drop, as we know, it forms adiabatic, the top of the cloud, suddenly it forms. After that, you need turbulent mixing to make everything happen. And see, there are a lot of things, the complexities are in this one. It's not just one thing or other. And these issues are well studied for many years. But the technique what I propose today is quite simple. And it's also validated using very limited observations what we have. There's a lot of potential as we go, look in the data set a lot more as we go along. But the key is that radar size, which is independent of any assumptions. And we have to validate that. How useful? I showed you some examples, but could we really make use of that to bridge the in situ measurement, remote measurement? There's a big gap. We're talking about small sampling volume like this compared to hundreds of meters sampling volume remote measurement. Then there's a big difference what you measure. Yeah.
Any other?
Yeah, you can.
Can you pass that back to me?
So I need to ask about the elephant in the room, and that is attenuation correction.
Yeah.
And so I assume you're probably using ocean surface backscatter to do that. Is that the case?
Okay. In this case, it is not. In this case, radar is looking up. Okay. Yeah, there are two ways to do it. One is you can use ocean referencing, could be done. Other way is you can look up. And in this case, basically, in this case, what I used was I showed EM simulations I showed you, how cloud and drizzle attenuation reflectivity. So with that, I did that. It's again assumption involved in this one. The NASA, the GPM measurement, they're already on ocean reference for attenuation measurement. That's all they're doing. But there's uncertainty because of wind speed, ocean waves, everything. But what you're going to do? That's the only thing we have at this point. You can make use of. If we measure the downlooking, then the independent attenuation measure, if you do it, uncertainty will be there. But that will be independent of some power law relations. We got to validate. But that's a good question. Hence, in remote sensing, like currently we do better than a dB calibration. Within a dB, we do that. About when we started working on this ESPOL radar, S-band, when getting a 3 dB, 2 dB is a big deal for us. John Hubbard worked on that quite a long time to make all things very good. And so, a lot of community people worked on that also. Those days, that's all we had it. ZDR, half a dB, that's all it. Now it's a 2/10 of a dB. Things have improved. And so this is the only way currently what we could do is if you have 2 radars, we can do better attenuation measurement. We can do that. But still, and scattering, the other issues with that also, sampling on the footprint, because both radars are different sampling footprint, how would you match? There are other issues. And so every technique will have pros and cons. But we could make the best use of what we know today. And it's like a GPM uses motion sensing. That's all they use it, 2 frequencies. What are you going to do? They generate tons of product. But what we have is a gold mine of measurements. That's what I'm thinking. 70, so about 20-meter resolution in the vertical. With about half a second means what, about 70 meters along the airplane track. These measurements are hard to come by, what we have.
Anyone else?
So just to follow up on Ricky's question, so yes, sometimes you can overcome some level of uncertainty with a whole lot of data, but if we can define what we can do with these products, so if your goal is to improve auto-conversion, parameterizations, and models, well, they're not very good, right? And so even with some uncertainty, in the products, what does that mean for what we need to learn to improve those parameterizations? And so that's a quantitative exercise that we could do with this and help modelers understand how they could use the data.
That's right. Exactly. I think, yeah, there's always going to be some uncertainty going to be there, but how we can do statistics, yes, I agree. And work with the modelers to understand how good are we in terms of finally the data assimilation and current schemes, yes. I think the opportunity, given that inform and current technique, what you're talking about, the scale sucker thing is a ESPAT, I guess, is the other thing you're talking about. The fantastic opportunity for EOL to contribute in various ways. And so I'm excited about next strategic plan, what NCAR working on this, asking us how observation going to contribute this cloud modeling, new weather prediction. I think you can offer a lot.
Good, you might have an assignment.
Thank you.
All right, I don't see any other questions online. So if there's no more in the room, let's thank Vivek one more time for that thought-provoking summary.